Right. So, good evening. This is, I think, the live interaction section of the first week for advanced computer networks. If at any point of time I'm not audible or my words are not clear, please feel free to stop me and ask me questions. And if you would like to also, if you don't feel comfortable talking, you can always go to your chat window here and you can type messages, which I'll look at and we'll respond to you. Right. Okay. So I believe all of you have, of course, taken advanced computer networks. It is under the assumption that you've also taken computer networks and you know certain basics of computer networks. Right. So the objective of these classes is to supplement your knowledge and to possibly help you solve the assignment questions uh, that you've been given this time or you will be given, right? So with that objective in mind, and also with the fact that this is the first live session, I thought we could revisit certain basics of computer networks and how the internet works as a whole, along with questions, of course. I'll be connecting that with questions. And hopefully this will refresh what you've done before and set you up for what you're going to see again, which is advanced computer networks, right? Right. So before we go ahead, a little bit of introduction of myself. So I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Hyderabad. So most of the materials that I've presented today is from the book Computer Networking, a top-down approach by Jim Firoz. So I believe everybody is joined. Let's take a look. Right. And yeah, most importantly, if anybody has to leave, feel free to leave. There's no okay. Goes automatically admit people, but okay. So if you have to leave, you can leave. You can join anytime. There are no hard and fast rules. How is it? Okay. Thanks. Is it clear now? Um, is it clear now? Or is it the same? Just change the position of the mic. No, it's not clear. Okay. Right. Okay. So at any point of time, if it is not clear, let me know. Okay, it's not clear. So what seems to be the problem? Is it a bit choppy, or is it that my words are not audible itself? Echo. Right. It's probably because I'm using two devices right now. Hmm, I think I can fix it. Give me a moment. Right, right. Yeah, yeah. I see it. My voice is not clear. Just give me a moment. Let me fix it. Is it by any chance better now? I think it should be better. You might not be hearing an echo.
Yeah, yes.
Now it should be clear, right? So basically, I think you might hear some disturbance in the middle because I'll be using my tablet to write on. I wonder how we can circumvent that. Um, I'll try not to use my tablet, but I think for some of these questions, it must. it should be used. But okay, let's see. Let's see. But as it goes on, let's figure it out. Right. Okay. So of course, the format of these sessions are going to be we're going to look at some questions and then look at the concepts of the questions and then answer these questions. Okay. So let's go to the first one. True or false? Application layer protocol encapsulates the transport layer message. Is this true or false? Just type in chat how many of these are true, how many of these, I mean, how many of you think it's true, how many of you think it's false. Okay, Kshitij says false. Is it? I see a lot of falses. By the way, this is the question. Right, I think, okay, a lot of falses. The reason is you have these layers, right? What are the 5 layers? You have application layer, you have transport layer, you have network layer, and then you have the data link layer, and then you have the physical layer. So the packet traverses from the top to the bottom. So this is where I thought I'll use a tablet. Let me try again and see if my voice is somewhat manageable for you people. Apologize. Maybe for the next one, I shall handle this aspect. Oh, you hearing the echo again, aren't you? Yeah, it is switched off. Thank you for the suggestion. It's still having this echo. I wonder why. Um, right, yeah, of course. Of course. I see. Is it manageable? Can we continue with this? Um, or is it and it, okay, let me just start explaining and then let's see how. Um, so we have the computer, correct? Okay, lots of people joining in. So we have the computer, and there are these 5 layers, right? So you have the application layer, the transport layer, the network layer, and you have the data link, and then you have the physical layer, right? So this might be a bit too basic for some of you people. Please bear with it. We'll take it from the bottom up. Right? So whenever you want to communicate with another computer, which is kept somewhere else, right? Let's say this is you, and you are typing in some data. You're saying hi, right? So this is the application layer message. And this application layer message is passed on to the transport layer, where it adds its header. It's called the transport layer header. And then this whole thing is passed on to the network layer, and another header is added to it, the network layer header, and so on. And essentially, the same stack exists in the destination computer as well, and it is decapsulated, right? So now let's look at the question. Application layer protocol encapsulates a transport layer message. So the problem here is the application layer is the generator of the message, right? As we saw, transport layer is not generating a message. Application layer is the one that's generating the message. So that is passed down to the transport layer, right? So the transport layer encapsulates so the transport layer encapsulates the application layer message and not the other way around. So you guys were right. It is false. This one is false. I think the next time you guys join, you will automatically be admitted inside. I'm not wrong. I think Bhakta, yeah, Bhakta Vachila, I think if you can mute yourself if possible. Can you hear me? Yeah, right. Question is not visible. Bhakta, possible you can mute. I'll fix some of these niggles that we're seeing right now. The next time we meet, I see that audio is a problem. I'll take care of it the next time we meet. And I also see that when I switch between the question to the explanation, you don't see the question, right? So I'll try to make it more consistent. All right. So bear with me for this first session. Okay. So now, so the second question, we'll read through the second part of this, which is the link layer protocol appends a network layer datagram with a link layer header to create a link layer frame. Right. So this is another layer below the network layer. And is it true or is it false? The link layer is below the network layer. And because of that, the network layer is okay. No screen is visible. Gosh. Is it? Right. Sorry. Now is it visible? Yeah, I think I can see my own screen, so I think this should be visible, right? It is visible. Right. Okay. Sure. Thanks. So I'll repeat this. These are very basic questions, very basic questions. We'll just move past it just to get you into the mood. So the link layer protocol appends a network layer datagram with a link layer header to create a link layer tree. So the link layer is below the network layer. So as we saw in the previous diagram that I just drew, that an upper layer sends the message to the lower layer, and that layer will encapsulate it with a new header. And that's what happens here. So this is also true. Right. So the answer here is true. Rajendra, hi. Is it your mic? I think it's your mic. Yeah, I think it's your mic. Your mic can be muted, I believe. Thanks a lot. Okay, so two people have joined just now. So just to give them an introduction, so they're going through some questions, some basic questions to get you into the networking mode, and we'll attempt some slightly difficult questions. They're not going to be difficult, but yeah, just right. Okay, so this is the second one. It's true. Now look at the third one. Only the end hosts implement all the layers of the TCP/IP protocol stack. Uh, I want you all to respond to this question and say whether it's true or is it false. Okay. I shall keep the question also nearby in case this is good. Oh yeah, this is better. Right. So I see some false, I see some true. So what is the answer? Feel free to interact, and if you don't want to interact, also it's fine. Just let's just have fun. So there are multiple aspects to this. Right. So the sentence has multiple uh, technical terms. The first term is end hosts. So what are these end hosts? And of course, you would have studied layers. I'm assuming because you've taken true underscore false. Okay, yes, I see that. That's an interesting answer. Um, that is an interesting answer. Oh, okay. And I also find a solution to admit people automatically. All right, so just bear with me for this first time. Okay, so someone is saying true and false. Okay, right. So let's go to the answer. So this is the question. I'll be switching over to my tablet to possibly talk about this question. Right. Third question. Sorry. Okay, good. I'm visible. Right. So the question was only the end host implement all the layers of the TCP/IP protocol stack. Okay, this is visible. Yeah, this is visible. Okay. Okay, so what are these end hosts? Is going to be the first question. So you have a computer. I'll represent the computer like this, right? And let's say you're sitting in your campus. This is, let's say, this is IIT campus. Here the sorry, right. Okay. And you want to access, let me say, google.com. So google.com is somewhere. It's somewhere else. It's in a different place. And that also has a server, correct? So this is the server. And your objective. Oh, okay. Someone is asking destination. Destination is a server. So now you are sending a packet from here. Just goes to, let's say, router. So this router is nothing but it's machine that is going to divert your packets in the right direction. And this is the big internet. This is what we call as the internet, core internet. The internet is nothing but a network of networks. It's a very simplified diagram. Don't take it as it is. This also has its router. So you have multiple smaller networks here. All of these have their routers. Right, so now you're sending your packet. You want to search for what was the cricket score today. Right, so you type in your Google query and then it does its encapsulations and everything. Let's not go into that right now. And it sends a packet. The packet goes over here. What happens here? The packet contains some information based on which this router is going to take a decision as to whether it has to send it in this direction or in this direction. Right? What is that information? Okay. Voice is not clear. I guess you'll have to bear with me the echo for today. Okay, right. So I think we have to bear with the echo when I'm explaining on the tablet. So sorry. um, so when is the next class? You mean the next class, next one of these sessions? I know one of your classes on Tuesday, which is mine, and I think there is one more class as well for the same. Whoever the next session. My session will always be on Tuesdays. But I think the other session is on Friday, if I'm not wrong. Oh, the session will be over around 8 o'clock. But as I say, you can feel free to leave at any point of time. There's no hard and fast rule that you have to be around for 2 hours. You can join, you can take whatever you need from this, and you can leave. And the recording will also be presented to you. So in case you're not able to join, you can see the recording, you can watch it at a higher speed, so that you can extract as much as possible in the shortest possible time, right? So there is no hard and fast rule. This is letting you know. Okay. The recording will be shared. So where were we? Right. Just bear with the echo for some time. It's this session. Let's remove the echo next time. Okay. So the question was only the end hosts implement all the layers of the TCP/IP protocol stack. Right. So as I was saying, you're creating a packet here, and the packet travels. Right? So based on some information that is encoded into the packet, it will be sent either in this direction or in this direction. There are a lot of factors there, and this process is called, actually this is called routing, but since you're studying about routers, also done through forwarding. Correct. Now, coming back to the core problem, right? So based on some information, it is traveling, let's say, over here, and then goes over here, goes over here, goes over here, and it reaches the end host. So what is this TCP/IP protocol stack? It is this 5 layers that talk about application transport, network, data link, physical, right? So which of all of these devices, this router, this router, this router, this router, this router, all the devices, do they, okay, who will decide which way to go in the router? Okay, so who will decide which way to go in the router, right? TP. Okay, so I deliberately did not say the answer to that. So there's something called IP addresses, right? So your packet, it has an IP address. So let's say an IP address. Give me an example of an IP address. 111.221.3.4. Let's say this is an IP address, right? So based on this IP address, this router will make a decision as to which way the packet has to go towards. How does it make a decision? The router has a routing table. And what are the entries in the routing table? I'm not going into extreme details here, just to keep it simple. So you have the IP address, which will be matched, and the output. So this output, let's say, is output 1, output link 2. So if it matches anything of the form 221.x.x, then please send it towards output 2. Or if it matches anything towards the form 112.3x.x, send it to output 1. Right? So this is what is already there in the routing table. Now, who has put it into the routing table? It could either be manual, or the routing table or the router can generate this table by itself. Right? It can generate this table. And there are also other cases where it's partially manual and partially automatic. For example, BGP. But I think it will be too complicated at this point of time. So we have the IP addresses, then we have the output links. This is output link 2, this is output link 1. So this packet is going and hitting the router. Okay. And the router is going to match this. And the longest prefix match is this. So it will send it to output link 2. Right? So that's how the whole internet actually works. It is just a set of routers that have come together that are somehow magically, okay, that are they're sending the packets for. Got it. Okay. So now coming back to the original question, which is end hosts. Right. So the end hosts in this case are what? This is a host at one end, and this is the host at the other end. Agreed? So these are the end hosts. End hosts are basically CPU-based systems in most cases. Right. Now the question is, you have end hosts over here, which is a server. The server is also a glorified computer. It's a computer with a lot of capacity. And a laptop is also a computer, but its capacity is not as much as a server. Right? The question is, there are many devices in this whole process. There are these routers in between, and there are these end hosts. Now, do all of these require the implementation of all the 5 layers? Is the question. Are all the 5 layers required in all of these routers? The answer is no. Why is that? Because you might have studied in your basic networks that the routing is done by the network layer. Right. The network layer header will contain the IP address, and the router only needs the IP address. It doesn't need to know what is there in the transport layer. It doesn't need to know what is there in the application layer. This is a simplistic design. So there are exceptions to this, but keep it like this for now. So it does not need to know what is there in the application layer. It has no concern about it. So why should I implement the whole stack on the router? So it won't. So what is implemented there are only till the network layer. Okay. So now that this one was one more question. Why not implement all the layers? Right. The major answer is the more heavy you make these routing devices, the more time it takes to route packets. Now I've shown you just like one packet that is going and hitting, but in reality, a router needs to handle a lot of packets, and it is in the order of TBPS in this case. In case of these routers, the order of TBPS, and to give you comparison to TBPS, right? You can search for it. Search for TBPS scale. That's huge magnitude. That is huge magnitude. That is huge magnitude. Terabits per second. The order of packets that are order in the sense the capacity, the amount of packets that are being handled by each of these routers. This router, high capacity routers. So what happens is every millisecond, every nanosecond is important. So you need to keep the software or the processing logic as short and as small as possible, which is one more reason why all the layers are not implemented in all the devices along the way. Right. So what is the answer to this question again? Only the end hosts implement all the layers of the TCP IP protocol stack. The answer is true. Okay. Now that was the simplistic answer, but there could be cases, there could be devices like middle boxes. That would mean that each router one second, I'm just admitting some people. Okay, that means each router knows on which memory address the IP is located. Is this address fixed? Okay, when you say memory address, I'm a bit confused, but I'll try to understand your question. You can feel free to unmute and have a discussion as well. If I don't know it, I'll go find out the answer and I'll let you know. Or if anybody else knows the answer, please feel free to have a discussion. Okay, that's the whole point of it. It's not a one-way communication. Anybody else can also raise their hand or just unmute and start speaking. Right? It's a free place. Okay, so coming back to Abhi's question, which memory address the IP address is located? Okay. When you say memory address, you're talking about the memory address of the router. Okay, data packets. And right. Okay. So you're saying how does the router know which part of the data packet contains the IP address? Is that what you're asking? I think that's what you're asking, right? Yeah, exactly. Okay. So that is why we have something called specifications. Right? So you have, let's say you have put a message hi, right? On top of this, you're getting a header. Okay. And this header is not random. If you are generating a message and if you are sending it through your computer and you are putting your IP address over here, okay? And if I am generating a message and if I am sending it across and I'll be putting the IP address here, then two systems will not know where it is. So the answer is yes, it is fixed. And this is specifications, meaning the first n bits will contain the source IP address, the next n bits will contain the destination IP address. So all of this is fixed. If you'll be interested to know, you can look at the header fields. Just you can just go to Google, you can type the header fields of uh, of network layer or the header structure of network layer, and you'll know what I'm talking about. So yes, your intuition is right. Uh, the structure of the header is fixed, which is why any device in the middle of the internet also knows where the IP address is. Okay, so I think that answers your question, right, Abhi? Okay, right. So now this is the third question. Okay. See, there's a way to. I'll just write it down here. Okay, so that I don't have to switch. Next time I'll have it in my tabs. A router on the internet doesn't look at the transport and application layer headers of the packet. I think from the previous explanation, all of you must know the answer to this right now. A router on the internet actually need not look at it. It doesn't have a need, but if it wants to, it can as well. If it wants to do some extra jobs, it can. But the answer to this question is true. Great, nice, true. Right. Okay. So I'll switch screens. Okay, switched. Right. So the answer to this true, true. Okay. So now let's just take a look at this diagram. This diagram is from a famous book, and that book is a top-down approach. Some of you must have read it. Some of you might not have seen it, but just to give you a view of how the internet is, right? So let's go through each of these diagrams. It just looks interesting, right? Let's look at the most easiest one. So this is your home. So you have your router, correct? Probably your provider would have given it to you, maybe Airtel or I don't know what's the other one, Act 5, someone. Um, So this is router, the Wi-Fi modem, Wi-Fi router, and then your laptop is connected to this, your fridge is connected to this, your um, let's say your thermostat or another PC as well. Okay, this is the home network. So this can be abstracted as a network. Similarly, there's another home, a smaller home, and they are connected. And all of these have upstream connections to either the local or the regional ISP. Now, what is an ISP? ISP is the Internet Service Provider. And let's look at some other types of networks. Let's look at something called enterprise network. So it is similar to a home network, but you have a lot many more number of end hosts. So this is an end host, this is an end host, this is an end host, end host, end host, end host, end host. You have many more, and you have many more network policies as well, because it is a professional environment. Essentially, it is all the same. It's just on a bigger scale. Now, interestingly, most of us also look at mobile networks, right? We rarely use Wi-Fi because we're not in our homes. We probably are staying outside somewhere. So these mobile phones and all these mobile phones connect to a tower, and this tower connects to a router, and that router once again connects to a regional ISP. And finally, you have data center networks. It's all different. So I mean, it might sound confusing for beginners, but these are all different types of networks. And the differentiation is not very linear. It is slightly a gray area, but you have to understand that the, the objective of these networks are different. Home network is to serve a few people. Enterprise network is to serve a slightly more number of people, and its functions are different. Now, coming to these data center networks, they are very different. They're wildly different. If you had so any query that you send to google.com or Facebook or any other let's say Netflix, right? So all of these go to a huge server farm that is kept somewhere at the other side of the world. These server farms are different. They have racks of computers. They are huge. They make a lot of noise. They are cooled a lot, and they're all kept. So this has a different topology, network topology inside the data center completely. Right? So they look nothing similar to the enterprise or the home network. But they are also in the end, they are also end hosts only. They also implement all the 5 layers. You see, questions? Right. So let's say this is we're talking about India. This demarcation is India. Now, if you want to go somewhere else, right? So you need to connect to another set of ISPs, which is the top tier ISPs. They're called uh, national or global ISPs. So essentially, what I'm trying to say is the internet is the set, an interconnection of different types of networks. That's it. All right. So with this context, let's move on. Which among the following companies fall into the category of tier one ISPs? There is AT&T, there is Verizon, there is Telstra, and there is Act FiberNet. Have you heard of these? Possibly not. So I'll just read through this one. AT&T, okay. So AT&T is the tier one. Okay, good. That's correct. A. There are multiple actually. Verizon is one more, and Telstra is another. Okay, because these are all.
Sir, which country? Verizon and Telstra?
Good question. Let me just Telstra. Okay, Telstra is Indian. Hmm. Oh, right. Sorry. I think it's Australia. Australia. It is headquartered at Australia. That's right, Australia. So, I mean, the question is for this particular uh, country, that is a Tier 1 ISP. That's the point. I'll show you another diagram which will be more clearer. And at FiberNet, uh,
Second tier.
familiar with it. That is the second Tier 1 because it's local, endemic to a particular city. I think Hyderabad has FiberNet, if I'm not wrong. We have multiple ones. I think a simple Google search would give you an answer. And all these questions are focused towards helping you understand what is the structure of the internet. Like, okay, now comes some interesting questions. There are a lot of aspects to this. Let me just do right. So how is peering link different from internet exchange points for interconnecting ISPs? So there are a lot of technical terms here, right? We just give you a moment to read this and parse the different technical terms. Okay, so what are peering links and what are internet exchange points and what are interconnecting ISPs, right? So basically interconnecting ISPs. So as I said, a network is made out of multiple ISPs. Okay. So let's start from the bottom. We have these access ISPs. You might have heard of some cable network providers who give you internet along with your TV,
Sir,
right?
I have a one question.
Yes, yes. Yeah,
Hello. In
yeah,
this
sure.
diagram, tier,
Mhm.
tier 1 is direct connected to Google, but the tier 1
Okay,
ISP, it is not directly linked with end user.
right, exactly.
I'm right?
Correct. Yes, you're right. You're perfectly right. It is not directly connected to the end user at all. Tier 1 is far up the hierarchy. What is connected to the end user is the access ISP. And this access ISP could be something like your uh, cable network provider. I don't know how many are familiar with this. Very small companies that provide you with internet. Let's assume one of them, you can see my pointer, right? I wonder how I can. Good. So let's say you are over here. This will be your connection. This will be your entry point to the internet. Now, now this Tier 1 ISP, it will be connected, let's say, to the data center through a similar such kind of process. Okay? Let's say the data center goes over here and somehow it's connected to the data center. Okay? Right. So you ask me that are we connected to Tier 1? No, we are not. So now, if you're sending some data packet, it will go here, and then it goes like this. Then it goes between the Tier 1 ISPs, and then it goes over here, and then it goes over here, and takes the same path back to you, possibly, or maybe not. We don't know, right? So that's how complex the internet is. But in the end, you get your answer in spans of milliseconds. Right. Okay, so the question was, how is hearing link different from IXP? Okay, so now this is the shenanigans when it comes to this level. So far, it is clear. Once the packet leaves your access ISP, there are a lot of interconnections. So you might have a regional ISP. Let's say this is Act 500. Okay. Now there are a lot of competitions, or you can say uh, negotiations that happen between ISPs itself. So the end goal for them would be to take the cheapest path to provide you with the data. For example, let's say you are here, okay, and you are sending a packet and you want to reach the data center here. So this regional ISP, right? This regional ISP, he has a choice. He can either connect only to this tier 1 ISP over here and send it in this longer path, or if he's intelligent, he will say, I want to connect to the IXP and take the shorter path. Right. So there are multiple options here. There are multiple um, uh, ways of reaching the same place. But what is the factor that stops them? It is economics. Pardon my handwriting, I'm just not able to do with the mouse. Economics. What if this tier 1 ISP says, for every packet, I will charge you $0.1 or 0.1 rupees? Okay. And what if this IXP says that I'll be charging you $0.2 per packet? So if you send the packet here, your users are going to experience a higher latency, but you are paying less money. The ISP is paying less money. But if we're sending it through here, ISP is paying more money, but the users experience faster internet. So see, there are a lot of aspects here. So this is where you must have studied something called the border gateway protocol, which also takes into account these contracts. So this is what they call as a contract between ISPs. Between ISPs are all contracts. Contracts that say, I will route your packets through my network. You send them to me. Right. So in a nutshell, this is pretty much how the internet works. Right. Now coming back to question, right? So the amount that a customer ISP, which means any ISP could be a customer at any point of time. This ISP is a customer of this ISP. Okay, I hope I'm not confusing you. There's a lot of technical terms here. So I'm over here, I'm sending packets to this ISP. I am the customer of this ISP. I am an end user. But this ISP is also not God. He also needs to be a customer of someone else. He also needs to pay someone else to route his packets through them. So that's where it happens when the amount that a customer ISP pays to a provider ISP. So this becomes the provider ISP for this customer ISP. Reflects the amount of traffic it exchanges with the provider, right? The amount it pays is directly proportional to how much traffic it goes through. Too much traffic, too much money. Less traffic, less money. So to reduce these costs, a pair of nearby ISPs at the same level of hierarchy, okay, this is one level of hierarchy, this one level of hierarchy, at the same level of hierarchy can peer. And this is that peering link. Imagine if this link was not there, any data that needs to be sent to the content provider over here or to the content provider has to go through the tier 1 ISP. But because of this peering link, the packet can go here, here, and here, and here, without reaching tier 1 ISPs. Tier 1 ISPs are costly, right? So there is this contract between these ISPs, which tend to reduce costs. And so to reduce these costs, a pair of nearby ISPs at the same level of hierarchy can peer. That is, they can directly connect their networks together. These networks are directly connected, right? To this network. So that all the traffic between them passes over direct connection rather than through upstream intermediaries. Meaning instead of going through here and going like this, it can just pass through here. Right? It does not need to use these upstream intermediaries. So also what happens is typically when two ISPs peer, when I was giving examples, don't take them literally. So this is one ISP, this is one ISP, and they are peering. This is what peering is. They connect directly with each other. This is called peering. This is clear? This is the peering link. The peering link. When these ISPs peer, it is basically a give and take policy. I will route your packets and you will route my packets. It's a win for you, it's a win for me. Your customers will get better internet, and so will my customers because I'm peering with you. Typically, when same hierarchy ISPs peer, they don't pay money to each other. It is settlement free. That is, neither of the ISPs pay to each other. But enter IXPs, Internet Exchange Points. These are huge establishments, right? So this is a place where multiple ISPs can connect and peer together. And these IXPs also ensure that there is connection between higher tier ISPs and lower tier ISPs, and possibly they reduce the costs. So if you connect directly to a tier 1, it might be more costlier than connecting to a tier 1 ISP through an IXP. So of course, an IXP earns its money by charging each of these ISPs that connect to the IXP. It's a relatively small fee, which of course depends on the amount of traffic sent to or received from the ISP. So essentially, if you look at it, the internet looks like a marketplace, right? So it's pretty much like a marketplace, and you pay money, and whatever fits their boat, they do it, and then they go ahead. So this is what, right? This is just a small introduction to, let's say, how the internet looks like. If you want more information, you can look at this top-down approach. It's in the first slide that I showed. It'll be in the recording as well, so you can take a look at it. Okay, now we previously saw a diagram, right? We saw a diagram like this. And then the big internet in the middle. Then you have cross boxes. Right. So what are these middle boxes? You heard of this term, middle boxes. Basically, middle boxes are anomalies, you can say. So they're not part of the standard networking components that are used in the internet. These are specialized to perform certain functionalities that are deployed at different parts of the network based on requirement. And they generally do not follow the standard protocol layering principles. Someone previously answered the question as true_false. Now, whoever answered that as true_false, Yeah, right. Om Dutt Mishra. So he was right because these middle boxes, they look at your application layer data, transport data, right in the core internet as well. So essentially, they implement the whole networking stack to perform various activities. So what are some examples? Some examples are firewall, NAT, called network address translator. People who've studied basic networks might be familiar with NAT, but it's too much for us to go inside what NAT is. I believe you must know what a firewall is. A firewall is nothing but um, it filters packets based on certain signatures that it sees. It helps you, and it helps secure systems, helps secure networks. And then you have load balancer. Then you also have deep packet inspectors. These are all the various different types of middle boxes that are in the internet. And where all can it be? And where all can it be? It can be anywhere on the. It can be anywhere over here. The middle box could be here. Middle box could be over here also. A middle box can be used by the local ISP. You can have a firewall here also. You can have, of course, everybody have all these routers have NATs. That's something. But a firewall could be here. A deep packet inspector could be kept here. The data center network. So there are all of these middle box devices that come into the network. That is why Omdat had answered it as true underscore false, because middle boxes tend to look at all the layers of the network header. Yeah, so that's why his answer is also right. Mm, right. Okay. Let's move on. Why is it easy for an attacker to impersonate any host on the internet? Is it easy for an attacker to impersonate any host on the internet? Yes, it is. Why? You can feel free to put some answers down there if you want to. So, so we know what a host is, right? And end host, we looked at an end host. A host is also generally looked at as an end host. So what does an end host have? It has an IP address. This IP address is what is put in the source IP of the header whenever it sends some data out to the internet. Okay. The source IP. So this number, right? This value, anybody can take a packet, put the same IP address of this particular machine and send packets, right? Are there any checks and balances that are being done in the middle of the internet against this? Absolutely not. At least not at this stage. Internet was not designed keeping security as a major factor in mind. It was designed for exchange of information in the most easiest possible way. Security was a far-fetched factor that they realized later was a problem. So essentially, on the internet, hosts are identified by IP addresses given in the IP packets. This is an IP packet. So a host in the internet can put the IP address of any host in the IP packet it generates and send it to the internet. And the receiving host cannot verify if the information provided in the IP packet is correct. It cannot. Right? So which is why it is easy for an attacker to impersonate any host on the internet. Okay. Now coming to a slightly more practical aspect of the internet. How many of you have tried traceroute or tracert? Can I just if you've tried traceroute, just say yes on the chat. Right. Abhi, you're right. Sorry, I didn't see your message. You're right, because of lack of authentication. That's the right word, Abhi. Thank you so much. Yeah, lack of authentication between client and server. That's why IP spoofing happens. Good. Okay, so Kshitij has used traceroutes. TP has used. Ankush has used traceroute. So I believe the majority have not used traceroute. Right. Okay. Now, for those of you who have used traceroute, try and answer this question. While doing a traceroute to a remote server, the delay measurement to a subsequent router can be lower than the previous router. Now, what could be the reason behind this? Think if you know the answer, just put it down in the chat. In the meanwhile, I will explain what traceroute is, so that everybody's on board. Okay, cool. So essentially, traceroute is nothing but it's a program. It's a program that's written into your system. On Windows, it is called tracert. On Linux or Ubuntu, on Linux-based systems, it is called traceroute. I believe most of you must be using Windows. So I put a screenshot of Windows. So what you have to do to perform traceroute, you just need to open your command prompt like this. Type cmd. This is your command prompt. And you just need to type tracert google.com. So this is for people who are using Windows. Now for people who are using Ubuntu or Linux, any flavor of Linux, you need to type in traceroute. You can do it as I'm doing right now. Okay, so this is not possible here in Windows. So the moment you do this, you're going to get a set of responses like this. And what we see here is what you're going to get over here. This is the whole screenshot of it. Right, so this is a question for people who are used to traceroutes. Right? Okay. So what happens in a traceroute? This is you. This is one router. This is another router. Another router. Another router. And finally, this is google.com. Right? Okay. So now what traceroute essentially does is it will find out how many hops are there for you to reach from you to google.com. Right? So in this case, 1, 2, 3, 4 hops. Fifth hop, I'll be reaching google.com. So that's the example that I've given. But in actuality, you are going through 12 hops. Okay. So, but now, how does it do? How does it do this? What is the strategy that traceroute does in order to uh, find out how many hops are there? Because if you send a packet, right, the moment you send a packet onto the link, the packet just goes here, here, here. It'll reach there, and you'll only get a response back like this. You won't know how many hops passed. So how does traceroute determine? How does traceroute determine how many hops are there? It's using a very simple tactic. So in the IP header, right, you have something called TTL, time to live. Have you heard of this? Not? Let's just take a look. Oh, can you see this? Maybe it is not the best diagram. So you see this TTL field. This is called time to live. Essentially, there is a number is filled in this TTL field by the host who is sending it. Okay, so here, here, here. I'll make sure the next time that the tablet is used properly. I'm struggling right now because of the discoveries that we made. This was the case, right? So this is sending a packet and it is setting the TTL value as 10, let's say. So every time the packet reaches a router, the TTL value is decremented. Here, once the packet is reached, TTL value is made as 9. Here, once the packet is reached, the TTL value is made as 8. Here, once the packet is reached, it is 7. Here, it is 6. And now it's on. So why are they doing this? Why are they doing this? The reason is, imagine somehow a loop has formed in the internet due to some misconfiguration. A packet will keep on getting routed like this infinitely. It's called an infinite loop. Just to avoid this, if there's a TTL value, it will keep on decrementing. And the moment the TTL value becomes 0, the packet will be dropped. Okay. But it will not just be dropped. A response will be sent to the sender saying that your TTL value is exceeded. Right. So now imagine if I'm sending a packet with a TTL value of 2. What happens? This packet goes here and it becomes 1. This packet goes here and it becomes 0. As TTL becomes 0, this router will respond to me. And when this router responds to me, I will have the IP address of this router. And voila, that's how. So first, it sends a packet with TTL value of 1, and then 2, and then 3. So 1, 2, 3, 4, 5, until it gets to the destination. And that is how you see this. This is the TTL value of 1, value of 2, value of 3, which means this is the first hop, second hop, third hop. fourth hop, fifth hop, sixth hop, seventh hop, eighth hop, ninth hop, 10th hop, 11th hop, 12th hop. Fine, we were there. Okay, but now the question is not that. The question is, these are all subsequent hops, right? You have a hop, the first hop, packet goes here, packet goes here, packet goes here, packet goes here, packet goes here. So ideally, the amount of time it takes, right? For the first hop, it takes 5 milliseconds and 2 milliseconds sometimes, and 5 milliseconds again in the sense. So for the first hop, it sends 3 such probe packets. These are all called probe packets. And it records also the time in which it got the response back from these routers. That's it. So first hop, it sends 3 packets. And let's say for all the hops, it sends 3 packets, 3 packets, 3 packets, 3 packets, 3 probe packets. With cheated values 3, 4, 5, 6, 7. I'm not sure if you're following along. What is meant by star? Yeah, right. Okay, coming to that. That is the next question, Neeraj. So the star, what is the meaning of star? Coming to that. It's not necessarily 0 milliseconds. So we'll come to that. So for the first hop, one packet, the first time it sent a probe packet, it got the response back in 5 milliseconds. Second time it sent the probe packet, it got it back in 2 milliseconds. Again, it got it back in 5 milliseconds. These are just 3 different experiments, 3 different times to send. That's it. Right now the question is, between these hops, right? Why are we observing the hop number 5 here is having lower values than hop number 4? That is the question. Can you see this? See, logically, it goes from 1, 2, 3, 4, 5. Right? So with 3, it travels a bit more to 4 and a bit more to 5. But if you look at the time it takes, 4 is a lot more than 5. Why possibly? How could this be? Is this possible? Yes, it is. That's why we're saying the live trace. But why? So that is the question. So I hope I've explained the question now. Would you like to try answering this question? The answer is very simple. Just think. I'll give you 2 minutes to think. If not understood the question, feel free to ask me again, but I can explain again as well. Right? Okay, so he did not understand. Okay, good. So let me do. The question is, this is me. That is 1, 2, 3, 4. These are all number of hops. Forget about this. So you're sending a probe packet from here. It goes here, and then it comes back. Right. And then next time you're sending another probe packet, it goes here, and it comes back. The time it takes for this probe packet to go and come back here is, let us say, 5 milliseconds. The time it takes for this probe packet to go to the second hop and come back, let us say, is 6 milliseconds. Now let us send another probe packet over here, and then it comes back over here. Right? But the time it takes for this probe packet to go and come back is 5 milliseconds. How is it possible? Is the question. Okay, who gives TTL first value? That is given by the host. Generally, the value is 64, I think. Yeah, the value is 64. It is a standard value because if you want to reach even from one end of the internet to the other end, you won't exceed more than 25 or 30 hops. So, but still, they give a safe value of 64. So for that, your packet will travel to any part of the internet. without um, without losing, without getting dropped. Right? So, but in this case, we are exploiting the TTL value, the TTL value. It's kind of like a hack, or in Indian colloquial terms, it's kind of like a jugaad, right? So we have our host, and we are setting the TTL value ourselves now. I'm not letting it go to the default value of 64. I'm making the TTL value as 1, and then 2, and then 3, so that I can force response from the first router, first hop, second hop, third hop, right? Now, but the question is, here I'm getting 5, here I'm getting 6 milliseconds, the time it takes, but here I'm getting 5 milliseconds. Is that possible? What could be the reason behind this? The answer is yes, it is possible. Because this hop number 4, this hop number 5. If you see, all the values that you observed here are less than hop number 4. So that's funny, right? The answer to this question is traffic conditions, network conditions. Right. So when you had sent the fourth probe packet, possibly there was more network congestion there, so it took more time. Possibly there were more packets being processed by this particular host, or rather this router, and that's why it took time to respond to your packet. Or sometimes queuing delay, lots link congestion, so many things. So the answer is traffic conditions. That's the only way. That's how possibly, when you send the third packet, this router processed it a lot more faster. It didn't take 6 milliseconds. It took 2 milliseconds, let's say. Then the packet that goes through here will come back more shorter than the previous instance. Essentially, that's the answer to this. Is it based on the size of the packet? I don't think so. Is it? I've not heard that perspective anywhere. Size of the packet is not, I think, involved in this as far as my current knowledge says. But I'll take a look at it if at all there is some validity to your statement. All right, KTP. Right. Okay. So now network congestion, traffic, or the processing capabilities of that particular host keeps changing dynamically depending upon the load on it. So it will give different values at different points of time. If I do the same thing again, we'll find inverted values as well. That's pretty much what it is. So traceroute is an intelligent way they use networks and network knowledge to find out how many hops it is. You can do so many things if you know network programming, where you can create your own packets and you can play with the networks. So all that the person is doing is sending some one type of packet, and he's finding out all this information about it. That's what traceroute is. Now, coming to the question that was asked, right? So what is meant by star? Star is nothing. It just says, see, the internet knows that there are a lot of people who are sitting and who are just sending packets. Traceroute is one such thing that uses something called ICMP packets. And these packets are low priority packets, meaning if the router is too congested, it drops these packets. So what some people do, if their router is already facing a lot of traffic, they will configure it in such a way that do not respond to any ICMP packet, which means star means this router did not even respond to our probe. That's what star means. It does not mean 0 milliseconds. It cannot be 0 milliseconds because there is a hop. After 5, 6 is a hop, 7 is a hop, but we don't know anything about it. We don't know its IP address because it did not respond to us. We don't know how much time it takes because it did not respond to us. So we move on. We assume, okay, we send 3, didn't respond, move on to 7. Right? So that's what this is. Okay, so any questions? Okay. What does request timeout means? And once request RTO flows, RTO appears, how we will move to the next hop? Oh, okay. Okay, so good question actually. Meaning you're saying once request timeout appears, how the packet will go next is the question, right? So the question is arising because you're assuming that we are only sending one probe packet. That is not the case. You know how many probe packets we're sending? This is one probe packet, this is one probe packet, this is one probe packet, this is another, this is another. So like this, like this, like this. So at 5, meaning if I'm sending another probe packet here, and I'm getting responses. So basically, the difference between these probe packets is this has all these three have a TTL value of 1. These three have a TTL value of 2. So my host computer, it will send this and it will move on. It's just that it knows for a TTL value of 6, I did not get any response, which means the sixth hop is not responding to me. That is what it is. It's not that one packet is what is going and responding everywhere. Once a TTL value is set to 1 and it becomes 0, that packet is dropped. It won't go any further. This first 3 set of packets will not go to the second hop at all. Right? Okay, so I hope that answered your question. You can take a moment to think about it. Right? So, of course, connecting it back to what you learned to speak, all of these, we're discovering routers on the way. Right? So these are all routers in the middle of the internet. Possibly this one is somewhere in the middle, sitting in the middle of the Indian Ocean or a transatlantic cable, possibly. We don't know. You can search for the IP address and see where it belongs to. It's interesting, actually. Right? Okay. Okay, now coming to some standard questions. So this is something called classless interdomain routing. Classless
Orbit.
addresses. Oh, okay, good. Okay, fast. It's 4. Okay, so take my time to explain. But you're right. The answer is 4. 5% right. Okay, I think I'll have to shift to my tablet now because writing on this is quite tough. Okay, right. So we are looking at this aspect here called routing, or rather, more importantly, forwarding. Okay, forwarding. So what is this done based on? What is routing and forwarding done based on? It's based on the IP address. And an IP address looks like this. It's got 4 octets, correct? Why is it called an octet? Because there are 1, 2, 3, 4, 5, 6, 7, 8 bits. Dot 8 bits. Typical 8 bits. 8 bits. Okay. So in this case, it will be 0. Correct me if I'm wrong. 0, 0, 1, 0, 1, 0. Am I right? And 0, 0, 0, 0, 1, 0, 1, 0. Correct? And then 30. Who can give me the binary representation for 30? it is. Zero, 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 and then one, one, mm, 40. Yeah. So this is 30. And then 0, 0, 0, 0, 0, 0, 0. Okay. So then you have something called a /28. Right? So what is the /28? So this /28 is nothing but a demarcation. Okay, it's like a distinction. Right? So I'm writing again. This is 10 dot 10 dot 30 dot 0. Okay, I've just written this in binary format. That's all, nothing else. Now let's start counting, shall we? So let's start counting 28. 1, 3, 1, 2, 3, 4, 5, 6, 7, 8. And then 9, 10, 11, 12, 13, 14, 15, 16. And then 17, 18, 19, 20, 24, right? 25, 26, 27, 28. Okay. So I'm drawing a line over here. Now what this says is this whole part, correct? This part plus this part will be called as the network address. So because 28 of it, 28 bits has gone to the network address, the first part is always the network address. How much is left out? There are 4. This is the host. So 4 bits represent the host address. But now let me change the question slightly and let's just say how many hosts are possible in this configuration. How many hosts are possible for this network address? Right, Abhi is right, exactly. 15, yeah, right. So one of them is broadcast, one of them is null. So let's say 15, 14. I'm not going to detail that. Somewhere around 15, 14, basically because there are 15 combinations or 16 combinations that we can actually make with these 4 bits. And some of them are reserved for broadcast. So it comes to 15, or rather 14 also, it's debatable. But let's not go into the details there. Just to understand that IP addresses are always represented in this format. And what do you call this as? So this /28 is also called a subnet mask, in the sense that in the router or in any routing table, you have subnet masks, right? So it is just a value. So in this case, subnet mask is 255, 255, 255 dot 40. Now in your free time, you can expand these values. These are all 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Or 240 is something at like 1, 1, 1, and 1. And the rest are zeros. Correct? So this is what the subnet mask is, and this is what it is. Now, if you take these two addresses, and then if you AND it with this, if you AND these two addresses, right? So what do you get? You get this value exactly. In the sense, the network address is going to remain the same. So what it will leave out is the last 4 bits. Sorry, it's over these bits and the last 4 bits, which will possibly be your uh, host address, which is your host address. Yeah, 28 bits is fixed for network ID. You're right. Regarding it's XOR operations. So this operation, it happens in the router, right? The router's engines. Okay, so I think these are all details that I didn't plan on going towards, but okay, it's fine. Time? Oh, yeah. 5 more minutes, and then if you have any questions. So these are all standard questions. Which of the following operations are performed when packets enter the ingress interface? Which of the following operations we were talking about routers, right? There's a router got multiple ports like this, and then input ports and output ports. So input ports is also called as ingress. Okay. So once a packet comes, the packet is inside the ingress, what it will do? It will look at the routing table. So I am calling this as a routing table because I want to keep it simple. But all of these aspects, whether it's a routing table or whether it's a hash table or whether it's a tree, whatever the implementation is, it is all abstracted as something called forward FIB. Okay? And this will contain, of course, as I showed you before, the outputs link. This link or this link or this link or this link. So it is consulted and it is determined. So of course, A. And right after that, you also need to do one more thing. You need to do something called TTL decrement. Can you link this with what we saw before? You were talking about TTL values, trace route, TTL values. Every router has to decrement the TTL value. This is a doctrine in the internet. If you are creating your own router tomorrow, you will also write a code in which the router will decrement the TTL value. All right. So I hope you're able to link this with what we saw before in traceroute. Right, exactly. This is for the previous question that Abhi is answering. Okay, so people have answered. Okay, good. Okay. Yeah. So basically, if you put all ones, that is for broadcast address. So it's actually 15. It's 15. Just what Abhi has answered. I don't wish to go and cover some broadcast right now. So yeah, so ACD, ACD, and D. But when you say D, right? When you say D, we are talking about the ingress interface. The ingress interface. It does not send it to the correct output port. That is for the egress interface, egress part of the router. So in the ingress interface, it just does this and this. That's it. This will also happen. Absolutely right. This will also happen in the router, but not when it enters the ingress interface. That's the difference. Okay. Shift it here. Okay, another true or false question. Which of the following trade statements are true? So the control plane operations are performed on every packet arriving at a router. The data path functions like output link scheduling and forwarding decisions are performed on every packet that passes through the router. The control plane functions are not performed on each arriving individual packet. So A is the converse of C and B is the converse of D. The answers for this. Take a moment to look at the question. So there are some technical terms. There is control plane, there is data plane, function data path, data plane functions. So I don't know what is your level of knowledge at this point of time. Since you've taken ACN, it's assumed that you would have taken computer networks also. I'm trying to not assume that and trying to explain things from the bottom up. So a router can also be divided into control plane and data plane. So this is a vertical division, right? So this division of a router can be construed based on the operations that it does. Okay, and this control plane does certain functions, and the data plane does certain functions. And one of the functions that data plane does is forwarding, meaning it just looks up the particular address on the table, finds out the output link, and then it sends the packet on the output link. So that is what the data plane does. And the control plane, it looks at slightly a higher abstraction. It could possibly do say the job of filling the routing table, like the routing table in the data plane. But who fills it? Someone with some brains, and that is the control plane. So depending upon how the control plane fills this table, packets will go accordingly. The control plane thinks that send this packet to some other destination. It can do it. It has some brains. So it takes these decisions based on certain inputs that it gets. Okay, I don't know how much more simply to put this as. Keep it like this. There's a control plane and there's a data plane. Okay, so BC are true. Yes, you're right. BC are true. So essentially, data plane operations have to happen for every packet. Because every packet has to be forwarded. So B is correct because the forwarding decision is required. And output link scheduling is also a part of the function of data plane. So it needs to be done because if the router cannot keep a packet that it needs to send it out. It has to send it out. So B is correct. But control plane function need not be performed every time. Only when the router feels, okay, I need to take a decision. Then it will run its control plane code and then take a decision and make an action and accordingly send packets forward. Right? So in essence, control plane is the brain and it does not need to be consulted all the time. For example, if you're signing, okay, you're signing on a piece of paper, okay, but you're not signing on just one piece of paper, you're signing on 100 papers. So when you sign the first paper, your brain, it's the control plane, said, okay, you have to sign. So you're signing. The next paper, you're mechanically going next. Sign, 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 sign. Right? You're not thinking in between. But suddenly someone comes and says, stop signing. You need to put a tick mark on all the sheets from then on. So you get this input from your brain. There's a control plane. Now, once again, you do an action, which is tick mark, tick mark, tick mark, tick mark, and all the other sheets of paper. So it's something like this. Not a great analogy, but it's something like this. So it's like that. So because this sign you're doing it on multiple, on pretty much all the papers, right, on all the sheets. But if you want to change the sign itself, then that is done by the control plane. It could be done by an input, by through the packet or through human intervention or through some other algorithm. We're not worried about that. But this change of ideas, right, change of routing, it does not happen for every. That's what it means. So B is true, C is true, right? So what are the goals for designing core routers to meet the increasing internet traffic? Meaning routers, right? We just saw how much packets can go through these core internet routers. So what are the goals? Is packet forwarding performance one of the goals? Yes, it is. Is scalability one of the goals? Yes. So by the way, what is scalability? Scalability is just a synonym to the meaning where you want to address as many as possible. So can your router can handle 10 packets per second, let's say, but can it also scale to perform 100 packets per second, process 100 packets per second? That is scaling. Scaling means going to a higher number. This is also a goal for core routers, right? So it needs to scale. And modular degradation, this doesn't make any sense. Of course, routers are modular, but you don't have to degrade any modules there. And availability, of course. You need the router to be alive. Right? If you're using your home internet and suddenly it stops because you're seeing that one of the lights are constantly blinking and it's stopping, it's not working, you're restarting the router. So that means availability is not there. It has failed in terms of high availability. Right? So it's A, B, and oh, okay. What's this question? Mm-hmm. If 20 or 0 dot. Okay, fine. Now, anyway, the time is over. So we'll just look at this question. I think we've covered pretty much. Yeah, these are all liquid questions. It's okay, fine. Let's conclude this session here and let's look at the next question. If you have anybody else has any question, you can ask. If I know, I'll tell you right now. If not, I will find out level. Okay. So, the question 20 has port number 3. Also has port number 3. Where is 20 dot? Okay. Oh, okay. So you're saying why? How come these two IP addresses are having port number 3? Same port number 3, right? So I'll ask you a counter question. Why not? Point is, see, where is 20, 20, 20, 20, 20, right? Any packet who is destined for 20.0.0.1 is sent through port number 3. And any packet which is destined for 20.0.0.2 is also sent through port 3. Because where is 20.0.0.1? It is over here. Where is 20.0.0.2? It is over here. So from this router, if this is sending a packet, this is sending a packet, and the destination IP address there is 20.0.0.1, should it send it over here or over here? With the shortest path, it has to send it to port number 3 only. And if it is 20.0.0.2, also it has to send it to port number 3 only. Why will it send it to 4? It won't. Right? Because 20 is over here. It can. You can go here, you can go here, you can go there also. But that's one hop higher. So from here, if you send it over here, 3, it goes over like this to 1, then again to 4. Port number 4 over here. Right? So it's possible. You just need to make sure the packets will go to where it's destined. That's the objective here. So with that objective in mind, if 10.0.0.1 is sending a packet with destination IP address 20.0.0.1, where will you send the packet to? If you think of this question like that, you will automatically fill 3. Again, if this is sending a packet with destination address 20.0.0.2, it will send a packet. It will send the packet where will it send it like this, or will it send it like, obviously it'll send it like this. Correct? Does that make sense? It's very much possible. Nobody said we cannot have it. So packet comes, it matches onto the first one, and goes to port 3. Packet comes, it matches onto the second, and then it goes to port 3. Port 3. Right? That's it. Um, Neeraj, is that clear? Okay, fine. Yeah. So think of the question like that so that you can see. In fact, a lot of this is slightly, if you take away the numbers, if you take away the IP address, right? If you put house address over here, if if you say, okay, this has a house address of this one, so which road will you take? If someone's coming here and they're asking you which direction should I go to if I want to reach this particular house, will you send them in the long path or the short path? Short path, right? So send them. That's it. Okay, fine. So shall we conclude? I'll hang around for another 2 minutes and then for another 5 minutes, and then you can ask me questions. If not, then you can if we leave. And yeah. So yeah, sure. Thanks. Thanks for coming. Yeah, thank you. Goodbye. Sure, Neeraj. Bye.